On May 22, 2018, an Israeli Air Force general walked into a press conference and said something that sent shockwaves through every air force on the planet. He announced that Israel had become the first nation in history to use the F-35 in operational combat. Not a training exercise, not a simulated strike. Real bombs, real targets, real enemy air defenses. At that point, the United States had spent 20 years and over $1 trillion developing the F-35 Lightning II, the most expensive weapons program in human history. And it had a problem that no amount of money could solve in a laboratory. It had never actually been tested against real advanced Russian air defense systems, until Israel did it for them. This is the story of why America's most guarded technological secret was handed to a foreign air force to test in combat. How Israel disguised the jet's true capabilities from Russian radar while simultaneously gathering intelligence on it, and why the Pentagon considers the arrangement one of the most valuable and least discussed strategic investments it has ever made. To understand why this arrangement existed, you need to understand what Syrian airspace looked like by 2015. When Russia intervened militarily in Syria to support the Assad government, it did not just send aircraft and soldiers, it sent its most advanced air defense infrastructure. The S-400 Triumph, NATO designation SA-21 Growler, a system capable of tracking and engaging targets at ranges exceeding 400 kilometers, at altitudes from extremely low to the edge of the stratosphere, simultaneously engaging up to 36 targets. Alongside it, the S-300 batteries already operated by Syrian forces. For context on what these systems represent, the S-400 is specifically designed to defeat stealth aircraft. Its radar operates across multiple frequency bands simultaneously, the theory being that a stealth aircraft optimized to defeat one radar frequency will inevitably be more visible on another. Russian engineers built it with American stealth technology explicitly in mind. By 2017, the airspace over western Syria was arguably the most heavily contested electronic environment on Earth. Multiple overlapping radar networks, layered missile systems, Russian electronic warfare aircraft generating interference across broad frequency bands, and Russian technicians watching everything, recording everything, learning everything. The United States wanted to know, needed to know, whether the F-35 could actually survive and operate in this environment, not in a simulation, not in an anechoic chamber at Edwards Air Force Base, in the real electromagnetic chaos of a genuinely contested airspace, against systems built specifically to find it. But there was an obvious problem. If the United States flew an American F-35 on combat missions in Syrian airspace, airspace where Russian military personnel were operating, where Russian radar systems were active, where a mistake or an incident could escalate immediately, the diplomatic and military consequences were potentially catastrophic. You do not casually fly your most classified aircraft into a de facto Russian air defense zone without risking a superpower confrontation. Israel had no such hesitation because Israel was already there. As we covered in our previous video on the F-22 ban, Israel had been permanently denied the Raptor, forced to make the F-35 work harder and do more than any other operator. And independently of American strategic interests, Israel had its own urgent reason to operate over Syria, the Iranian weapons pipeline. Throughout the Syrian civil war, Iran had been systematically moving advanced weapons,
anti-ship missiles, precision surface-to-surface rockets, air defense systems, through Syrian territory to Hezbollah in Lebanon. Israel viewed this as an existential threat and had been conducting a sustained covert air campaign to destroy these shipments, known as the Campaign Between the Wars, or in Hebrew, Mabam. Israel was already flying combat missions into contested Syrian airspace, already navigating Russian radar networks, already striking targets in one of the most electronically hostile environments on the planet. The Pentagon recognized what it had: a real-world combat laboratory, operated by a highly capable ally, flying America's most advanced jet against exactly the threat systems the U.S. most needed to understand. The arrangement that followed was not publicly announced. It did not need to be.
To understand what made Israeli F-35 combat missions so valuable to the Pentagon, you need to understand what the F-35 actually is. Most people think of the F-35 as a stealth bomber, an aircraft that sneaks in, drops weapons, sneaks out. That description is technically accurate, but fundamentally incomplete. The F-35 is, at its core, a flying intelligence collection platform that also happens to carry weapons. Here is the best analogy. Imagine a person walking through a crowded room while every sensor in their body, eyes, ears, skin, is recording everything simultaneously, and a computer is instantly processing all of it into a single coherent picture. That is approximately what the F-35 does with electromagnetic energy. The system is called sensor fusion. The F-35 carries multiple independent sensor arrays: the AN/APG-81 active electronically scanned radar, the AN/AAQ-40 electro-optical targeting system, the AN/ASQ-239 electronic warfare system, and the AN/AAQ-37 distributed aperture system, which essentially gives the pilot a 360-degree spherical view around the aircraft in all lighting conditions. Individually, each of these systems is extraordinary. Together, fused by the aircraft's central processing architecture, they create something unprecedented. Every radar signal that hits the F-35's hull is analyzed: frequency, pulse rate, scan pattern, power level, geographic origin. The aircraft builds a real-time three-dimensional map of the entire electromagnetic environment around it. Every radar source in range is identified, characterized, and located. When Israeli F-35s flew combat missions over Syria, they were doing something beyond dropping bombs on Iranian weapons convoys. They were flying through the active emissions of Russian S-300 and S-400 systems that were searching for them, scanning across them, attempting to track them, and every microsecond of that interaction was being recorded. The exact frequencies the Russian systems used, the specific scan rates and patterns, the moments when the radar painted the aircraft and the moments when it lost track, the blind spots in the coverage, the reaction times of the operators. That raw combat telemetry flowed back through secure channels to Lockheed Martin and the U.S. Air Force. Software engineers used it to update the F-35's electronic warfare libraries, the onboard databases that tell the aircraft how to respond to specific threat systems. Frequencies the jet had never encountered in testing were added. Countermeasure sequences were refined. Radar-absorbent material performance was validated against real emissions rather than estimated ones. The feedback loop worked in both directions. Israeli pilots reported handling characteristics, system behaviors, and maintenance issues under sustained high-tempo operations. Lockheed's engineers pushed software updates back to the fleet. Problems that would have taken years to discover in peacetime testing were identified and fixed in months. The Pentagon was, in effect, running the world's most expensive and most dangerous software beta test, with Israeli pilots as the testers
and Syrian airspace as the server. But there was a problem with this arrangement that kept American intelligence officials awake at night. If Israel was flying F-35s through Russian radar coverage to gather intelligence on those Russian radar systems, those same Russian radar systems were simultaneously gathering intelligence on the F-35. Every time an S-400 painted an Israeli Adir, it was recording something. Not necessarily getting a strong return, the stealth was working, but recording the absence of a strong return, recording the exact radar cross-section signature of the aircraft at specific frequencies, specific angles, specific altitudes. Over time, with enough sorties, Russian analysts could build a profile, a map of exactly where the F-35's stealth was strongest and where it degraded, the specific angles and frequencies at which it became slightly more visible. That information, in the hands of Russian or Chinese radar engineers, would be worth more than almost any other intelligence they could obtain. It would allow them to tune future radar systems specifically to exploit the F-35's weaknesses. The solution was a device called a Luneberg Reflector, and it is one of the most elegant pieces of deception engineering ever fielded on a combat aircraft.
A Luneberg reflector is based on a principle discovered by German mathematician Rudolf Luneberg in 1944. It is a gradient index lens, a sphere or partial sphere constructed from concentric layers of material, each layer having a slightly different refractive index for electromagnetic waves. The geometry is precisely calculated so that any radar signal entering the device from any direction is focused, reflected back, and returned toward its source with dramatically amplified intensity. In plain terms, it is a device that makes an aircraft appear vastly larger on radar than it actually is. Israeli F-35s flew many of their Syrian combat missions with Luneberg reflectors physically bolted to the airframe. Small, lightweight, easily attached and removed on the ground. The effect was strategic deception of the highest order. To Russian radar operators watching their screens, the F-35 appeared as a large conventional aircraft with a normal radar cross-section, not a stealth jet, just another plane. The operators were recording a falsified signature, a deliberately corrupted profile that bore no resemblance to the F-35's actual stealth performance. The aircraft was simultaneously bombing real targets and gathering real intelligence on Russian radar systems, while feeding those same radar systems completely false data about its own capabilities. Think about what was happening in that airspace at once. Israeli pilots were navigating Russian air defense networks. The F-35 sensors were recording every radar emission. The Luneberg reflectors were transmitting false stealth data back to those radars. Bombs were falling on Iranian weapons shipments. And in the background, secure data links were streaming everything back to American intelligence analysts and Lockheed Martin engineers. It was not a combat mission. It was a multi-layered intelligence operation that happened to include ordnance delivery as one of its secondary functions. The Russians watched, they recorded, they analyzed, and according to U.S. intelligence assessments, what they concluded was that the F-35, based on what their radars were telling them, was not particularly more stealthy than aircraft they already knew how to track, which was precisely the conclusion Israel and the United States wanted them to reach. There is a concept in military aviation called mission-capable rate, the percentage of aircraft in a fleet that are ready to fly a combat mission at any given time. It is the most honest measure of whether an air force can actually sustain operations in a conflict, rather than just perform impressively in peacetime exercises. For the United States Air Force, the F-35's mission-capable rate has been a persistent source of concern. Supply chain delays, specialized parts shortages, and the sheer complexity of the aircraft's maintenance requirements
have kept U.S. readiness figures in ranges that the Air Force itself has publicly described as insufficient for a sustained high-intensity conflict. The Israeli Air Force, operating in a condition of persistent near conflict with no tolerance for unready aircraft, developed solutions to these problems that the U.S. military is now studying seriously. The difference comes down to a fundamental contrast in operational philosophy. The U.S. Air Force maintains aircraft for a theoretical future conflict. The Israeli Air Force maintains aircraft for a war that, in practical terms, never fully ended. That distinction drives every maintenance decision, every spare parts stockpile, every training protocol for ground crews. Israel integrated predictive maintenance software into its F-35 operations earlier and more aggressively than any other operator, using the aircraft's own sensor data to anticipate component failures before they occurred, rather than responding to failures after grounding an aircraft. They developed indigenous repair capabilities for components where U.S. supply chain delays were unacceptable, working with Lockheed to gain maintenance authorities that other operators don't hold. They restructured crew schedules and tooling availability around the operational tempo of actual combat, rather than the administrative tempo of peacetime operations. The Pentagon is now formally incorporating Israeli F-35 maintenance doctrine into U.S. Air Force readiness planning, particularly in the context of a potential Pacific conflict with China, where U.S. aircraft would need to sustain high sortie rates from dispersed bases far from established logistics chains. The scenario planners wargaming a Taiwan contingency are looking directly at how Israel keeps jets flying under pressure. The nation that was sold the F-35 partly to serve as America's combat laboratory has become, in at least one domain, more operationally proficient with the aircraft than its manufacturer's own Air Force. The student has become the teacher, and the teacher is taking notes.
Step back and look at what the United States actually purchased with the decision to sell Israel the F-35. America got real-world performance validation of its most expensive weapons system against the specific threat systems it was designed to defeat, without risking American pilots, without triggering a superpower confrontation, and without revealing the jet's true capabilities to the adversaries monitoring it. America got a continuous stream of combat telemetry that its own testing programs could not have generated in decades of peacetime exercises. Software patches, electronic warfare library updates, maintenance protocol refinements, all of it battle-tested, all of it validated under conditions that no simulation can replicate. America got an ally operating the F-35 at a sortie tempo and readiness rate that is now teaching the U.S. Air Force how to sustain the aircraft in conflict conditions it was actually built for. And Israel? Israel got the most capable strike aircraft in the Middle East, modified to its own specifications in ways no other operator was granted. It got the ability to independently strike targets across the region without asking for American permission or American aircraft. It got the deterrence that comes from operating a jet that its neighbors cannot match and cannot adequately track. Both sides got exactly what they needed. The arrangement was not charity, it was not sentiment, it was a calculated strategic exchange negotiated between two governments that understood precisely what each was receiving. The most expensive beta test in history cost the United States a foreign military sale at preferential rates and a willingness to share classified technology with a trusted partner. In return, it received a debugged, battle-hardened, combat-validated fighter jet without losing a single American pilot in the validation process. As returns on investment go, it is difficult to argue with the math. Here is the question I want you to sit with. Should the United States formalize this kind of arrangement, deliberately deploying advanced weapons with trusted allies specifically to gather combat data before American pilots need to rely on it? Or does sharing that technology, even with allies, create risks that outweigh the intelligence value? There's a real argument on both sides of this issue. I want to know where you land. Drop your answer in the comments, and if you've been following this series on the weapons, the deals, and the engineering decisions that quietly shaped the modern world, the next one is already built.